Hi friends, welcome to my channel. Let's have a look at the newly appeared problem 2645, minimum additions to make valid string. In this video, we're going to analyze it using a stack. So in this video, we're going to first write a short solution, and then we're going to expand the short solution to be a longer one to digest the details. So for the short one, we're going to explain how we design the code, and for the longer one, basically it reveals our thought process. First, let's look at the problem statement. So here we are given a string called word, to which we can insert letters A, B, or C anywhere and any number of times. So we are required to return the minimum number of letters that must be inserted so that word becomes valid. So a string is called valid if it's a multiple of ABC in the sense of string, right? So here we have three examples. First, I'm going to look at example 3, because example 3 is basically a multiple of ABC, because it's here ABC repeats once. So in this case, it has a full match, so we're going to return 0. So this is the one. Now let's look at example 1. So in example 1, the length is less than 3. So here we have only one letter, that is B. So in order to make an ABC, so we need to have A and C inserted from beginning and appended from the end. So we're going to output 2 for this example. And here in example 2, so the word has length 3, and all the letters are A's. Because of the definition of validness, so we need to have 3 ABCs. So in other words, we should have BC times 3, right? So in other words, we make an ABC for each of the A's. So we have 2 times 3, that is 6. This is for example 2. So now, after we look at the 3 examples, let's look at constraints. First, the length of this word is bounded above by 50, right? This is a small number. The word is not empty. Secondly, the word consists of letters A, B, and C only, right? So even the word, if it were an empty, right? So we want to make it valid. If we assume the empty one is not valid, then we can make one ABC, right? So that will have a return 3. So that's, but due to the constraint, that's an invalid case. But it's good to be aware of that. So with that said, we're ready to look at the analysis or solution. So here, actually, once we understand the patterns, it's actually relatively routine to design the coding, right? So here we use the word design because if we can understand the details as to what kind of formats or representations to write the code is at our disposal. So here, let me just to give some hints so that we can write the code, then explain backwards. And then after we explain the code, then we can share a longer one, which actually aims to reveal more details. So here, actually, we can examine the results or the outputs for the following strings, for strings like the following. So if it's an ABC, right? So you just return 0, right? Or if it's a BC, right, we just need to return 1. So if it's a C, right, so we just need to return 2. So in this case, the returns is 0, 1, and 2, right? So here, I consider C first. And then if we consider the strings A and B, right, so let's consider, say, AB, right? So in this case, we just need to append a C, right? If we have a B only, we need to append A in front and C behind. So we're going to have 1 and 2. This is the return. So if we have letter A, right, so we need to return 2, right? So in other words, what we want to do, we can do the match. We match the backwards, right? So we match C first, and then match B, and then match A, right? By first checking C, and then checking B, and then checking A. So here C and B and A are the single letter strings. You're just writing like this way. So with that done, basically you can come up with a solution. So here, let me first present one solution, and then we're going to use this example to explain the code. So basically, this 6 strings, special strings, they compose the problem. So any word will be a combination of these 6 strings. So once you can solve all of this, so you can solve any string. So this is basically a decomposition and conquer strategy, I would say. First, let me initialize a result variable. So this result variable is going to be used for counting. So we are going to return the final state of this variable. And then we are going to make the word a list. So this is just a type conversion. Like in the previous video, right, we convert list to set and convert list to a dictionary, right? That's for efficiency. So now but here this word conversion to a list is for this logic, also for using the stack. So I will say in this one we use stack to aid our counting. So now with that said, let's initialize a variable. So here 2. Basically, I want to do the match and match with these characters. So A, B, and C, right? So I'm going to first match C. So if I match a C, then I'm going to match B, and then I'm going to match A. So this is our sort. So we're going to start from 2 because 2 corresponding to this index. If we match the C, we're going to decrement the I to be 1. And then if we match the B, we're going to decrement this by 1 again to get 0. And then if we match the 0, so then we're going to make it 2, right? So this is the circular thing. Essentially, you know, we're matching ABC, ABC, right? So now let's do the while loop for matching. So while word. So here, let's see. Let me make some remarks. So this is the matching and counting. So this part contains the core logic, right? So basically, we want to check word -1. So if it equals characters I, so actually you can first keep this example in your head for looking at the code. You can imagine the word is nothing but ABC, right? So if it matches, so then we're going to do word pop, right? So here, this operation is always valid because our while condition is word is not a empty list, right? So we can call word -1 so that we do not have an index problem. So if this is the case, otherwise, if it does not match, so we're going to increment this result by 1, meaning that we need an additional character to match this. So then after this, so we're going to you can first ignore this else. For example, if you match the C in the word ABC, then you are going to decrement this I by 1, right? And then what we are going to do, so if we match the B, then if we match the A, right? So we are finishing 1, then I will be 0, right? So if we still do decrement, I will be -1. Actually, we need to start another round, right? So basically, if I equals 1, and the word still not empty, we need to reset I to be 2. So in other words, we are matching 2, 1, 0, the 2, 1, 0. This is the periodic thing, right? And then what we are going to do, So we're going to increment the result by I plus 1 and then do the return. So let me explain why we do this. So you can imagine this is BC for the word. If the word is BC, you can match the last one, that is C, right? So you pop that. So then the index I will be decremented by 1. Now you have index I equals 1. Then you can match B, right? So we matched B, then you get I equals 0. But at this time, so we match 2 characters, but the word is empty now. So we are left in 1. So in this case, I is 0. So we need to increment by 1, right? This is the one explanation. So now let's look at this case. If you have a word which is C, right? So you can match this C, right? Then you decrement I by 1. You are going to have I equals 1. But this word will be empty, right? So I exited with a state 1. And then we match the 1, so we need to add another 2. So here we have I plus 1. Right, that's 2. So this matching this C. So, but now you can also using A, B, and B and A to check the code. So, for example, if we use B to check, right? So because the first one is C, does not match. So you're going to increment the result by 1. This adding of 1 will be representing a letter C, right? Then we decrement I by 1. Then I will be 1. But the 1 will match B and 0 will match A. Then the word will be empty, right? In this case, I will be negative 1. So this will be 0, right? We have 1. That's corresponding to AB. So overall, so you can check this code will work for all these 6 strings. So it's going to be right for any word or any combination or any concatenation of this 6 substrings. And then we're going to return the result variable. So this is our first solution format. So here actually we want to demonstrate that we can actually, for this medium problem, it's not it's a very routine one. So we can directly using abstract sorting reasoning to get this coding format. However, if we know how to decompose into smaller problem, and then we can treat all these cases, then we can treat all. So this is the one problem solving strategy. So now let's look at the test. It passes this one, right? So we checked A, B, C, and then let's check the generic case. It passes all the cases, all the test cases. So this is the one solution format. But this code is in some sense is compact, right? So because we designed this, so if in this case you can still use the character to be you set character to be ABC, is still okay, right? Because you just indexing this string, but using list is also a good one. But here the thing is the order, right? So this is the one solution format. So after we explain this solution format, let me explain or show you the second solution format, which is an expanded version of this code, right? Then you can compare the two formats of coding to see the logic. So I actually include that part here. This is the version 2. So I'm going to change this one to be the solution. And then here we are using stack, and we want to analyze to digest the details above. So basically, let me quickly review this problem. We initialize a result variable as above, right? Then we use a stack. So basically, we made a list type conversion. Then basically, if the stack is empty already, so we are going to just return 0, or because in this problem the word is assumed not to be empty, right? Then we're going to check the current character. So if the current character is a C, right? And then if the stack is empty, so we know we need to add AB in front. So we are going to increment this result by 2. the else block will treat the case that the stack is not empty. So now let's see, if the stack is -1, so we're going to pop this result, this character A, right? So we have a C, we have a A, so we need to insert a B in between. So we're going to increment this result by 1. So this is the if block here. The else block, if it's a B, right? So if it's a B, right? So we have a C in front. So we want to do further check. So if not stack, so we know we currently have a BC substring. We need to add a, right? That's why we increment the result by 1. This one corresponds to a character A. And then we also pop this B, right? And then if the stack is not empty, then we're going to pop this one, right? So because this is the B, so we have a BC already, right? So if not stack, so we're going to just add 1. This again corresponding to A. Now if the stack is an A, right? So -1. So we have ABC, we just pop without anything. All the other cases we're going to increment by 1. So this is the one. The other else block, so we have C, but we have other letters, for example B, we have for example C, right? We're going to increment the result by 1. So this discusses the case the current is C. And actually if the current is A, so no matter what, so we're going to add BC afterwards. So we need to increment this result by 2, right? Then the other case, this is C, this is A, this corresponds to B, right? So if we have a character B, and if the stack is empty, so we need to add 2, because we have to add A in front and the C behind. So otherwise, if the stack is not empty, so if the stack top element is A, so we have an AB, so we just need to add a C after the B. So we just pop the current A and increment the result by 1. So this one corresponding to a letter C. All the other cases, we just need to increment the result by 2, right? So this is the logic. So actually this code is the same code as the code here. But for the second solution, it's not very direct to write this logic in a clear hierarchy. So that's why we present this solution format. So actually I first wrote the solution here, and then we did a detailed analysis to write this solution. The second one is a little bit verbose. However, I sort of emphasize this one. So once you have this one, you can actually do some optimization to get the first one. That's why we at the very beginning we are discussing how we design the coding or the format. So with that said, I guess that's about it for this specific problem and this video. Thank you.